Yes, now there it is. So we're coming back for more, and we'll follow up with another recorded talk with Rob Richardson, who will be talking about Async Python, good it is, where we'll see how easy it is to do multiple tasks in one, and how we collect all the results. We'll also look at the best practices and edge cases, like how to start an asynchronous process from main. Uh, well, um, Rob is a software craftsman building web properties in ASP.NET and Node, React, and Vue. He's a Microsoft MVP, published author, frequent speaker at conferences, user groups, and community events, and a diligent teacher and student of high quality software development. He's a MVP, and well, you can find his task and other talks at his blog. So we'll continue along with him.
Hi, welcome to Pyjamas. Today we're going to take a look at Async Python. We'll get to look at a lot of code and how Async I/O works. Here's the part where I tell you I am definitely going to post the slides on my site tonight. I've been that person chasing the speaker, which is why you can go to robrich.org and the slides are online right now. Let's head there. We'll go to robrich.org, we'll click on presentations, and here's Async Python good it is. The slides and the code up on GitHub are online right now. Achievement unlocked! While we're here on robrich.org, let's click on About Me and we'll see some of the things that I've done recently. I'm a Shoreline developer advocate helping people to maintain Kubernetes. Docker and Microsoft have each given me some awards, and I'm also a friend of Redgate. AZ GiveCamp is really fun. AZ GiveCamp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver completed software to charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp, or if you'd like a GiveCamp closer to you, find me here at the event, or hit me up on email or Twitter, and let's get a GiveCamp in your neighborhood too. Some of the other things that I've done, I've published a few books, and one of the things I'm particularly proud of is I replied to a .NET Rocks podcast episode. They read my comment on the air, and they sent me a mug. Woohoo! So let's dig into Async Python. Now, this is really fun. Let's first start with what is asynchrony. Now, asynchrony is being able to do more than one thing at the same time. Kind of. It's really about doing those things independently. We can do two processes that run independently and can reach their own termination points separately, which means we don't need to wait for each to finish before we start the next. Asynchrony, we can think of two independent things. By comparison, synchronous, is one thing after another. Why would we choose to do asynchronous behaviors? Well, it's different depending on whether we're on the client side or on the server side. For server side, we can leverage our hardware more effectively. So, for example, if we're in a synchronous world, we might divide our server equally, and you get one particular pie. By comparison, with asynchrony, we can yield our thread and let others use that piece of the hardware to be able to accomplish their task when we don't need it. On the client side, we're doing asynchrony to be able to do more than one thing at the same time. So imagine opening two documents at the same time. Now, if we had a synchronous process, maybe we could only open one document. We'd have to close that one to open the next one. So why wouldn't we do asynchrony? Well, synchrony is a lot simpler. Just doing a sync thing, we can read from top to bottom in our method. It's a lot clearer, a lot simpler to be able to execute. And one of the big things with synchronous behavior is we completely avoid race conditions. Well, what are race conditions? Race conditions is where we mutate shared state, and usually we can end up in some pretty awful concerns. So for example, let's imagine these two different developers or two different programs running simultaneously. Now the first one says, if the file exists, then load the file. Well, let's imagine that it checks to see if the file exists, and then the second program makes the file exist. So the first program doesn't believe the file exists and then shows you the message even though it does exist. Or let's flip this one opposite, and let's check to see if the file exists, and it does, and then the second one deletes the file. Then the first one goes to load the file and gets a file load error because the file doesn't exist. How is this possible? Because we're mutating shared state. We have a race condition. The way to avoid race conditions is either to run synchronously, not have the two pieces in the same spot, or not mutate shared state. So strategies for asynchronous things. There's lots of different ways that we can do that here in Python. We could do subprocess.popen and run another executable. We could do threading.thread. And so let's take a look at each one of these. First off, popen. Now with popen, we can just launch another process, which means we can start anything. Is that Python? Is that a shell command? Is that a Go app? It doesn't matter. We're just launching whatever we launch. On the downside, we have no visibility into that process. We can get standard out and standard error. Maybe we can stream that into place. But at the end of the day, really, we don't have any visibility into what that process did other than its exit code. And that exit code can be pretty opaque. 0 is success, non-zero is failure. But we don't have any way to pass variables between them. We don't have any way to understand how far along it is. This is a very opaque process. By comparison with threads, we get a whole lot more visibility. We can share variables between the threads. We can launch these threads and have them run in parallel. We can take a look at the things, and we can even pass messages between them, set variables, and read it on the other thread. On the downside, this process is ripe for, well, synchrony, race conditions. Debugging this is a nightmare, and the setup of threads is really awkward as well. It's very difficult to get this process to run effectively, and the code is, well, really verbose. So when we look at both of these mechanisms, we realize that asynchrony is really hard. And it is one of those things that we want to do to better leverage our hardware, but it's really hard to code. Now let's take a look at Async I/O. Async I/O was built to be able to solve these kind of problems, to make it easy for us to program asynchronous code. Async I/O is great at being able to think synchronously and run asynchronously. That's excellent. So in theory, we ought to be able to get the best of both worlds. We get an asynchronous program, but we get a program that reads more or less top to bottom. That's cool. Now, Async I/O, it was clearly inspired or stolen from C# and JavaScript. It has identical syntax to them, which is great. In the same way that in C# and JavaScript, the compiler builds up this state machine, in Async I/O, the compiler will build up this state machine that is resumable. So once I finish this step, I can go off and do some other work, and I can come back and I'll start off with the next step. Now, all of this happens transparently just with the async and await keywords. Let's take a look at that code. Here's an Async I/O program. So we can see that we import the Async I/O library. We'll start some stuff. We'll call into some function, but we have the await keyword here. So it will go do that asynchronously, and whenever it finishes, we'll continue grabbing our results. Now this is an asynchronous function so that it can do that awaiting, and now we have that mechanism for being able to do asynchrony, but make it look synchronous. Excellent. So Async I/O, it's a lot easier to reason about than other methodologies. We can think synchronously, but it still works asynchronously. Now, Async I/O is not truly simultaneous. It isn't launching new threads, it isn't creating parallel processes, but it's great for I/O-bound tasks where we're doing a lot of waiting for things. If we're waiting, let's yield this thread and let somebody else use it for a while. Once this process is done, then we'll pick up and continue on. If we really do want two compute-bound processes to run in parallel, then async is not the right solution. So Async I/O, it is great for I/O-bound workloads because we're waiting for the result. But it's not great for compute-bound workloads because it's not actually running at the same time. Rather, it's just context switching between the two processes. So how do we install Async I/O? Well, we don't even need to pip install this. Starting in Python 3.4, it is built in. So we just need to import the library at the top of the code file, and we've got asynchrony. So here's an async program. And we saw this a little bit previously, but we can see how this program, we just add an await keyword saying we're going to go do some asynchronous work, and we'll have an async keyword documenting our function. So let's take a look at a code sample here. Now these code samples are up on GitHub, so you can come in here and you can run each of these samples. I'll open it up in VS Code. Let's start out with the hello world. We've got that synchronous method here, asyncio.sleep. So it's going to just go off and do the sleeping thing, and we'll just run it. So Python 1, and we can see that it does that asynchronous work. And our program run length is 1 second. Now what's it doing in the meantime? Well, in this case, it's just sleeping. It's not doing anything. But we could just as easily wait for a database call, or wait for an API call, wait for another function to finish. That worked out well. We have this asynchronous function that is able to go off and do some other work, and once it finishes, we get the results in a really simple way. We don't have to grab exit codes and standard out and standard error. We don't need to do thread.join. We can just do our program as if it was a synchronous program, but it runs asynchronously instead. Now, one of the rules of asynchronous methods is that we can only await other async methods. And we can only have an await in async method. So it is kind of viral in that nature, where once we have an async method deep in our tree, then all the rest of the methods calling it also need to be asynchronous as well. Now, I did put an asterisk here because there are ways to overcome that, but for the most part, that's the methodology that we want to use. If we have an await, it needs to be inside of an async keyword, and if we call an async function, then we need to await it. So let's take a look at some sample use cases of how we might use async and await. We saw that hello world mechanism, and the cool thing is this asynchronous method will just go do the things that it needs to do. Now we do need to kick off that process, kick off the asynchrony, and so we'll do an asyncio.run. Now we'll probably do this at the beginning of our program just to kick off the event loop and get it started running asynchronous tasks. If we just called main directly, it wouldn't actually have that event loop running, and our asynchronous program wouldn't run as expected. But we saw how this program worked out really well. We can just sleep for a second, and then once we're done, we'll continue on. Let's take a look at another use case. Now in this case, we're looking for a database call. So we'll grab async IO. We'll also grab IO MySQL. And so now we can do MySQL database calls asynchronously. So we can see lots of awaits here where we're creating mechanisms where that process may take some time. This is excellent. We don't know how long the database is going to take to execute this command, so we'll just await it. And then we'll go grab the next row, and we can validate that that works as expected. We also close the close the connection, and wait for that connection to be closed as well. So we'll asyncio.run that to be able to kick off the event loop, and now our database connection will run asynchronously. Perfect. Now, most of the time we will use the async and await keywords. And probably most cases that will be completely sufficient. But what if we need a little bit more? Let's look at some use cases that might be a little bit more advanced where we might use other primitives. As we talk about these, we'll talk about some other keywords here in this mechanism. A coroutine. Now, this coroutine is a function that has async def at the top of it. So it's not just a regular method, but rather, well, an async method. Now, we can talk about a coroutine object, the results of calling that method. Then we have a future. A future is a promise of a future result. In JavaScript, these are called promises. In Python, they're called futures. Now, this promise of a future result is the results of calling an asynchronous coroutine. So that coroutine object, we can think of that as a future if we wrap it nicely. And so the way that we'll wrap it is in a task. If we take a coroutine object and we wrap it in a task, now we have a variable where we can check the status, see if it's done, and get the result once it's done, and even cancel it. And fourth, we'll have the event loop. The event loop is the process that keeps track of those asynchronous processes, and once they're done, it calls into that callback, returning the results of that state machine. So we do need to kick off the event loop, but for the most part, after that, we'll forget about it. So let's take a look at each of these things. We have a coroutine that is an async def function. We have a future where we get the results of it. Notice that this is a runtime error, so that won't actually work, but that's actually the result, that future. We can async io.create task, wrap that future in a task. So now that we've got the task, we can either await it or cancel it or check to see if it's still running. And then finally, the event loop. We need async io.run to be able to kick off that process. We'll probably do that exactly once in our application just to ensure the event loop is running, and then everything else we'll just use async and await, or we might use create task. Notice though that with that task we can still just await it to be able to get at the result. Coroutines, futures, tasks, event loop. Yeah, the majority of the time we'll just use async and await, and we don't need to worry about any of these. So let's talk about interop with existing code. Now, most of the time, we'll have those rules that say if we call into an async function, we need to await it, and any function with an await in it needs to be an async function. But, well, what about some of the extra things? If we have a, say, main function, we need to be able to kick that off. And so we'll use async io.run to be able to start that event loop and get that started. For example, here's a main function and it calls into my function. So it needs to kick off this asynchronous process, but then it wants to go do the other main things. Now in this case, we didn't await it and we didn't async io.run. So this process will start, but it will not continue. We'll start running, we'll do this async io process, but we never check to see if it's done. So this line at the end never runs. So that's definitely not the right way to do it. Instead, the right way to do it here is we'll do an async io.run, and now it will do the thing, and then it will finish running this main method, and then it'll finish sleeping for a second, and then we'll get still run at the end. Let's see if we've got a sample for that. Async io from sync. Yep, here we go. We're going to call into that function and then ultimately finish. So Python 3. We can see how it runs. It's still running, and main is running there too. So we've kicked off that asynchronous process, and then we can continue on doing the other processes that we need to do. Excellent. Now, probably we don't need to worry about the event loop other than to make sure that it's running. So calling async from synchronous code. The best rule of thumb is don't do it, but we probably do need to do it once to get our code started. The benefit of just awaiting it is that we get the results, we get exceptions if any of those happen, and all of that just happens in line. By comparison, if we call asynchronous code from synchronous code and we just say async io.run, then we don't get those results, we don't get the return codes, we don't get exceptions caught. So we do need to kick off the process. So we'll probably say async io.run main, and that will kick off our event loop and ensure that everything else in our application can run asynchronously. Why do we need to do this? Because we can't async the Python executable because that's really not how that works. So instead, in the top of our program, we need to async io.run our main method. Great, now that we've got that event loop running, everything works great. So let's take a look at some other advanced techniques where we might want to take a little bit more control over our asynchrony. Now here we're trying to do two things at once. We have this do work function that will sleep for a specified amount of seconds. We'll print messages before and after, and we want to launch it twice. Let's launch it first for 2 seconds, then let's launch it a second time for 1 second, and we'll await in both places. Now, if we launch this sample, we can see that we've got that waiting for 2 seconds, waiting for 1 second. So let's Python 4. The total execution time of this application is 3 seconds. We waited for 2 seconds, and then we waited for 1 second. These things didn't happen in parallel. Now, our application did yield to accomplish other work, perhaps, but because we're awaiting these straight away, they're not running in parallel. Let's take a look at how we might do this a little bit differently. So let's have this do work function, and let's asyncio.createTask. This task now lets us handle other things. So we'll launch the first one, the 2 seconds one, we'll launch the second one, the 1 second one, and then we'll await both of them separately. We've launched both of the processes, they're continuing to run, they're continuing to wait for their results, and now we'll wait for their answers. Now in this case, we're waiting for the second one and then the first one. We could do that in another order, or we could await an array of tasks, but we'll see here, Python 5, that now the total execution time for this program is 2 seconds. It doesn't do them one after another, it does them both simultaneously. Well, kind of. It context switches between them. So how might we do this if we wanted to do a whole lot of things? Well, here's another one where we do that same wait for a certain amount of seconds. And so now let's kick off the 2, let's kick off the 1, and then we'll asyncio.gather. This will take an array of futures and turn it into an array of results. Once it's done, we can just await that asyncio.gather. So now let's do this, Python 6. And we can see that we'll kick off both of them, we'll wait for them. Now in this case, 1 was done first and then 2 was done. That's totally fine. And so our total execution time was 2 seconds. Now, should we use asyncio.gather or should we just await the 2 of them? That's definitely personal preference, but ultimately it yielded the same result because we said create task and kicked off both of the processes and then came back and awaited them, then they ran in parallel. Alternatively, we kicked off and gathered them in the same spot and got our array of results. So when we kicked them off and then awaited both of them after that, it did work in 2 seconds rather than just in 3 seconds in our original example. And here's that other way of doing it, asyncio.gather. So how do we gather these results? Well, whether we're awaiting multiple things or whether we're doing asyncio.gather, the rule of these tasks is that it will succeed when all the tasks are complete, or it will throw on the first error. So if we called do work and one of these do works failed, we wouldn't continue waiting for the other one. We would just immediately throw that exception, and then we could handle that error elsewhere. So what if we only want to wait for a certain amount of time? So in this program, we have our do work that will sleep for a certain amount of seconds. And so let's call that do work and have it sleep for 10 seconds. But then let's say asyncio.wait for. So it's going to run it, but it's going to time out after 2 seconds. If after 2 seconds this program doesn't finish, then we'll get an exception, a timeout error. But if it does finish in time, then we'll just continue running. So let's run that one. Here's this program where we're going to wait for we'll launch it for 10 seconds, but only wait 1 second. So Python 7. We can see that we launch it for 10 seconds, we wait for 1 second, and we gave up waiting. We ended up here in this exception. Well, what if we do that a little bit differently? Let's launch it for 1 second and wait for 2 seconds. Now, if we launch this program, we can say that we finished waiting, and so we didn't throw an exception in this case. It finished in time. This can be great if you have, say, a long database call or a long API call, and you're not quite sure if it'll finish in time, and you want to provide a good user experience. Now, it doesn't actually cancel that work. It just gives up waiting for it. So does that work continue? Maybe. Will the task complete even though we're not waiting for it? That's not deterministic. If our program exits, maybe that thread gets aborted, or maybe we're closing a socket and then the server may not notice. It's not deterministic. Will it finish? Will it not finish? Yeah, because it's not deterministic, we should probably not use this for updating data. Let's take a look at canceling the task. Here we're going to want to abort that process to make sure that it doesn't finish. We have that same do work function that will sleep for a certain amount of time, And so now let's create that task, and then let's wait for that task. But if we don't want to wait long enough, then we'll call task.cancel to abort that work. So let's take a look at how that would work. Here's canceling the task. And so we've got that create task. We'll wait for, notice that instead of just calling the method straight away, we've already wrapped it in a task, so we have more visibility. We'll wait for 2 seconds, and then if we give up waiting, which of course we're going to do, we're going to give up in 2 seconds instead of waiting 10, then we will cancel that work so it won't continue. Python 8. So we launch our task, in 2 seconds we cancel it, and now we've exited doing that work. Now, how about that thing? Is it done? Did it finish? Is it going to get stuck in the middle? Are we going to end up in an indeterminate result? Well, yeah. If we cancel the task, how far along the road did it get? Did it add all the rows? Did it only add some of the rows? Did it change all the data? Did it not change the data? It's a non-deterministic result. And so, especially if we're calling into an external API, then that external API may do things completely differently. Will it notice that we've closed the socket and end that work? Will it end it in a good state? Ultimately, it's probably best for us not to cancel a task unless we know that that task is running a pure function. It's only querying data, not updating data. If we're updating data, we probably should not cancel. We should probably see that through so that we get a deterministic result. Ultimately, if that's going to throw an exception, then we know that that update did not complete. But if we have a pure function, if we have a GET request, then perhaps we can cancel if we're tired of waiting for those results, or if we have a new query that may replace the old query. Async IO. Async IO is a great library that allows us to think synchronously and run asynchronously. That's really great. It allows us to get the best of both worlds with asynchrony. We can code asynchronously, but we still can reason about it as if it was a synchronous program. We just decorate our code with async and await, and we're able to take advantage of it. Now, there are additional scenarios where we can dig deeper into running parallel tasks or canceling tasks, and those are definitely available to us. And Async IO is built in. Thanks for joining us here for Pyjamas. This was fun to dig into Async IO inside Python. The slides and the code are online right now at robrich.org. And I'll join you in a moment for that spot where the conference is designated for live Q&A. Or if you're watching this on demand, hit me up on Twitter at robrich.org and let's continue the conversation. Thanks for joining us.